So we're on to question 2. It's a complex numbers question. It says the complex numbers z1, which is -2 or -2 plus 0i, and z2, which is -1 plus 2i, are plotted in figure 1 on the Argand diagram for the complex plane, where z is equal to x plus iy, so real number plus imaginary number. It says plot z3. 1 plus I on the Argand diagram above ensure the point is clearly labeled. Well, I'll be hoping any student doing higher level even sort of maths will be able to plot Z3, and that was an easy 5 marks. Find the modulus of this complex number as of Z2. Z2 is -1 plus 2i. So you can use Pythagoras' theorem or the square root of the real part squared plus the imaginary part squared. You're going to get root 5. So we're up to 10 marks. So that starts off nice and easy, but it gets a bit more complicated here. And this is the part that might have scared students away from this question. It says, show that arg z2 minus z1 over z3 minus z1 is equal to pi over 4. So with this, this looks far more abstract from the part that they've just done, clearly, part A and B. However, if you know your complex numbers, you'll be able to do this as well. We know when dividing complex numbers in polar form, we know that you end up subtracting the arguments. So it's going to be the same idea here, that the argument of z2 minus z1 divided by z3 minus z1 is equal to the argument of the top minus the argument of the bottom. So let me just highlight that for you there, just to show you where that's all coming from. So z2 minus z1 is our kind of numerator, and z3 minus z1 is our denominator. So the argument of the entire fraction is the argument at the top minus the argument at the bottom, and again coming from division of complex numbers in polar form. So we better figure out what z2 minus z1 is. Well, z2 is -1 plus 2i, z1 is -2, and of course you can have the plus 0i in there if you wish. Putting that together, then minus 2 is obviously going to become a plus, so you'll have -1 plus 2, which will give you a +1, so you'll have 1 plus 2i. You will then have, so you can see that up here, that is z2 minus z1 on the Argand diagram, and then z, if we want to actually figure out the angle, so z2 minus z1 is our point up here. This is our 1 plus 2i up here in the Argand diagram. So if we want to figure out the argument, which is the degree of rotation anti-clockwise from 0 degrees, well, using inverse tan to find theta, I can say, well, theta is equal to the inverse tan of the opposite over the adjacent 2 over 1, so the inverse tan of 2. I can say, then I'm going to do a similar idea here for z3 minus z1, so that I know z3 is equal to 1 plus I. Again, z1 is equal to -2, so I'm going to be saying -2, which again will give me the +2, so I end up with 3 plus I. So over here on the Argand diagram again, z3 minus z1 is going to be 3 plus 1i, or 3 plus I. If I want to find out my angle here, my argument, I'm getting the inverse tan of 1 over 3. So now I'm going to say, show that the argument of z3 minus z1, z2 minus z1 over z3 minus z1 is equal to pi over 4. And what you're going to do is you're going to just keep going here step by step until you get to your answer. So we're going to say it's the inverse tan of 2 minus the inverse tan of 1/3. And if you want to put that into your calculator, you're going to find that you get your answer, which is pi over 4. And of course, you want to have your calculator in radian mode. So that's 10 marks for that. But if you kind of go at it step by step, you will get to your answer for it. So you're on to 10 marks. Okay, So we have our final 10 marks to go. We're up to 20 out of 30. But we have a look back here. It says write Z3, which is the complex number that we've found over here. Write this in polar form, r cos theta plus I sine theta, where r is an element of the real numbers. Theta is between 0 and 2 pi, and hence simplify Z3 to the power of 4. So this is a good old-fashioned De Moivre's theorem. So we know that it is 1 plus I, so it's 1 out and 1 up. We can figure out what r is, the modulus. It's the square root of 1 squared plus 1 squared is root 2. We can figure out the argument here, which is the inverse tan of 1 over 1, which will be 1. The inverse tan of 1 is 45 degrees, or pi over 4. And we then say, well, Z3 can be written as root 2 times cos 45 plus I sine of 45. So now Z3 to the power of 4, whether we have the whole of the right-hand side raised to the power of 4, because the left-hand side got raised to the power of 4. So the right-hand side gets raised to the power of 4. We now apply De Moivre's theorem. So the modulus gets raised to the power. So you end up with root 2 to the power of 4. And the arguments get multiplied by the power. So you get 4 times 45, which is 180. So you get 4 cos 180 plus 4 times sine of 180, 4 times 4I sine of 180. The cos of 180 is equal to minus 1. So 4 times minus 1 is minus 4. The sine of 180 is equal to 0. 4 times 0 is 0. So you get minus 4 plus 0I. And that, of course, is my final answer. And that was worth 10 marks as well. So a mixed bag of a question, all connected here to our diagram on the right-hand side, but it went from very straightforward into quite abstract stuff, and then back to something that you'd be quite familiar with at the end, the simplifying complex numbers in polar form. Okay, so that's question 2 complete. And now we're on to our third question